Hello everyone. Now today we're going to take a look at the capacitor resistor network. When you have a capacitor and a resistor connected to a power supply, that capacitor will charge up in an exponential fashion based on this value here and this value here. Now it's not a linear charge. It doesn't charge from 0 to 10 volts in a straight line. It charges up something like this. When I throw the switch for that 10 volt power supply across this circuit right here, it charges up something like this. It comes up real fast and then it starts to slow out until it reaches a full charge. This is an exponential graph right here. It's not straight. There's a little bit of math involved here, which makes this a lot of fun because you can see in the physical real world how the math works out. We'll go down here and we'll look at the math. It's real easy math, nothing hard. Now this right here is the formula. It's called tau. Tau is capacitance times resistance. And that's the time constant, the charging and discharging time constant, and it's in seconds. Now here our circuit had 1000 microfarad and 10,000 kiloohms. So to determine tau, we just multiply 10,000 microfarads times 10 kiloohms, and it'll give us tau in seconds. So here's microfarads all drawn out or as farads. 0.001 farads is 1000 microfarads. And here's our 10,000 ohms. And do a real quick shortcut in math here. We see that our 1 is on the right side by 3 decimal places. So if we go over to the 10,000 and we bring that back 3 decimal places, we have the value 10. And that's our tau. 10 seconds for 1 tau. Now here it takes 5 tau to fully charge or discharge a capacitor resistor network. That means that to fully charge or discharge our circuit, it will take 5 times 10 seconds or 50 seconds to fully charge and discharge our circuit with those values of 1000 microfarad and 10 kiloohms of resistance. That is neat, isn't it? That is fantastic. Where you can take a physical circuit and watch the math work itself out. That's amazing. That is amazing. We'll go up here and look at our circuit again. We're going to breadboard this circuit, and we're going to watch the time to discharge and the time to charge that capacitor right there. That capacitor and resistor network. We'll watch it charge up and we'll watch it discharge. Now if it charges up exponentially, what do you think when we discharge it? It'll discharge exponentially also. That is amazing how that works out. It'll be something like this. We'll be at 10 volts up here, and we'll discharge in an exponential fashion down to 0 volts. So here we charge from 0 to plus 10 volts, and here we discharge from plus 10 volts down to 0. Here's another equation that you can use. This equation right here will tell you the voltage across that capacitor at this instance in time. This is the voltage across the capacitor is equal to E in parentheses 1 minus E raised to the negative T over tau. E here is the final voltage across that capacitor when it's fully charged. Little e here is Euler's number of 2.718. T is the time at that instant in seconds. It is the time that you want to determine the voltage across that capacitor. And tau is the capacitance multiplied by the resistance. Now in our circuit, E was 10 volts and the capacitance was 1000 microfarad and the resistance was 10 kilo ohms. This is the equation for the charge cycle. Isn't that fascinating? You could take a time slice of when this capacitor is charging up and find out what the voltage across that capacitor is at that time. That's amazing. Now there's a similar equation for the discharge time. Very similar. The difference being that we don't have the 1 minus here. So the voltage across the cap is equal to E in parentheses Euler's number, little e, raised to the negative T over tau. That's for the discharge cycle.